In this installment, we want to make a momentum time graph of the phenomenon we just observed. We just calculated in the previous installment. So we have time, we have momentum, we have zero. Now what we knew in the beginning is we had a momentum of -6. And refresh you, the calculations we had at the bottom, we had initial momentum of -6, momentum of 6 afterward. And this collision occurred over 0.2 seconds. So we have a momentum of -6, and then it makes contact in the wall. We don't know how long, but it makes contact over a period this delta t of 0.20 seconds. And after that is done, it has a momentum of 6. Now, we know at this instant in time, it is at this location. At this instant in time, it's this location. The question might be, what happens in the interim? Now, one possibility might be it's just a straight line like this. Another possibility might be like this. And a third possibility might be like this. The result is the same. Well, let's now try to, maybe it might help us to figure out what's going on in this delta t of 0.20 seconds. And take a look at the origin. We found where the origin is. Great. We know we're located right here in the Cartesian plane. The y-axis is momentum. The x-axis is time. We can read anything to do with momentum and time. The slope is delta p over delta t, which is the rate of change in momentum. And the area is going to be p times t. P times t. Now let's see. P times t is going to be kilogram meters per second times second. So it's going to be kilogram meters. So this is kilograms is mass, and this m meters is like the distance mx. It's sort of like the center of mass, the weighted mass of the object. It's kind of like that. So not really that useful, the area. All right, so now the slope, we said, is the rate of change of momentum. We want to think about this physically, what's going on. This ball comes in, it hits the wall, and it slows down, and at some point, the velocity is 0. The center of mass of the ball is 0, and that's right here. So that's when it comes to a stop. Now, and looking at the slope, our first case says the rate of change in momentum is constant, meaning the change in momentum from -6 to +6 is occurring at the same rate every tiny increment of time. This second case says it starts out changing very quickly, slows down in its change, has very slow change, and then its rate of change increases considerably, and then decreases again. So I'm drawing the tangents there at those locations. Whereas the green one says it changes very quickly at first, then not very much at all, and then it speeds up again. And it goes from changing very quickly to none at all. The rate of change of momentum is changing very quickly here and then not at all because the slope is 0. So you can see, probably you have an intuitive feeling that this green one just doesn't look right. This goes from no change to it's got extreme change in momentum, and then it's not slowing down very much. The question then becomes, is it at an even rate or more like the red curve? Well, in your experience, if you have a ball that is going to compress, if you take a ball in your hand and compress it, and you compress it a little bit, it's hard to do. And then if you want to compress it the same amount again, that would be the same delta x and the same delta t. That's going to be harder, isn't it? As you compress it further and further, it gets harder and harder to change that dimension. So it's got a bigger breaking power as it gets closer and closer to its maximum compression. So the rate of change is not going to be constant. It's going to be steepest when it's at the 0 point. And that's why this is the way the curve looks. That's why that's the way the curve looks. And you can also see it's smooth around this transition point as opposed to like catastrophic, discontinuous change even. So that's how we would graph that. The most important thing for you to be able to get, of course, is getting this and this correct, having this correct delta t. You can reason through this to get to the red. So now we want to use a vector diagram to determine the change in momentum. So the change in momentum is P minus P0. Well, we know we can say the sum of the momentum is P plus P0. That one is easier to do. So we have our final momentum, which is this, 6 kilogram meters per second. That's the afterward momentum. Plus the initial momentum, which is this, minus 6 kilogram meters per second. This says we started here, and at the end of the first one, we added that one, giving us a resultant of 0. Is the sum of the momentum 0, the before and after? Yes, we had minus 6 before and 6 afterward. The sum of those two is 0. But we know the change in momentum is minus 12. When we are subtracting vectors, we have P plus a negative P0. There's no such thing as subtraction. There's only adding a negative. So instead of subtracting P or 0, we're going to add a negative. Now, a negative on a vector is the opposite direction. So we have P, the initial P, which is, or the final P, which is P, like so, 6 kilogram meters per second. And P0 was this. That's P0. But we want the opposite of P0, which is in this direction. This is negative P0, which is negative of negative 6, which gives us an overall resultant of 12 kilogram meters per second. So this is how we make a momentum time graph and how we can figure out the change in momentum in terms of vectors.